So this is important if you are in chemistry or biology. You see here you have a dipole. So one here is positive Q, here you have negative Q. So it's the same charge, so the same amount of charge in coulombs, except one is positive, the other one is negative. And that will be the example of water molecule. Right? Water molecule is a permanent dipole. Why is that? Because hydrogen gives away its electrons. So on that side, you're going to have a negative charge, positive charge because it lost electrons, and the oxygen is taking the electrons, right? So if you look at uh, hydrogen H2O, you see you have oxygen and hydrogen. Hydrogen is giving away its electron. So hydrogen here on that side, you have plus 2Q. Oxygen will be taking the electron. So you have minus 2Q. Okay, so this is called a dipole. So for the hydrogen molecule, okay, on one side you have minus 2Q, and on the side here you have 2Q. Okay, and it's a permanent dipole. So you see here that configuration, what you see. So if I ask you conceptual question, an electric field always starts at a positive charge and at a negative charge. And when you look at this configuration, you see that the electric field is trying to bring the two charges together to lower the potential energy of the configuration. So it's behaving like a stretched spring. It wants to bring the two charges together. Okay, it's like it's being stretched. Now it wants to bring it together. Okay, so this is very important and it's called a dipole. In chemistry, you have a lot of dipoles. So if you go back to the slide 42, you see you can visualize the electric field of a dipole. So this one, you have two electrodes, so they are connected to a power supply. So that will be connected to the plus of the power supply, that will be connected to the minus, for example, and you can have those in some kind of oil, castor oil, and inside here you have non-conducting material like seeds, right? Or rice, very tiny. And that way you can visualize the electric field. So this will be called a dipole. So for example, if you have Q here minus Q, okay, the electric field go from plus to minus. So that will be the electric field of a dipole. And as you move away, you see the electric field lines. We trace them farther away because it's going to be weaker. So this is plus, I said. So plus, it's going to be here. It's going to be along the line. And here it's going to go in. Is that clear? So that here you can visualize, for example, a point charge. Now, do you remember something we talked about and it's called polarization? Do you remember polarization? So if, for example, here you have a plus charge, okay, we understand we're going to have an electric field here. Positive charge is like a hair dryer. It's a source of an electric field pushing, blowing away. Okay, so remember, if I put a positive charge on electric field, what is it going to do? With the electric field or against a positive charge? Oh, very good. Okay, it has a positive mind, it's just a follower. If you have a negative charge, it's going to go against, because that way the goal is to lower the potential energy of the charge placed into the electric field. What you see here are little seeds. So they are not conducting. Okay, so they cannot move. So if I place a seed like this, it cannot move. But this is plus. However, what it will do, even though it cannot move, it will twist, okay, because it will be polarized. So this side will become minus, this side will become plus. Do you remember polarization? Like if you put a balloon here, the balloon, let's say it has been positively charged. Remember, it's not conductor, it's not a conductor, so the charges cannot spread all over. But if you bring it close to the wall is also a conductor, but here it's going to have the molecule inside the wall, it's going to be polarized. Okay, so it means the electrons, they cannot move because it's inside the conductor. They are not allowed to leave their nuclei. However, those molecules can be polarized. So same thing here. Those little seed here will get, first of all, there will be a torque applied to it, and they have to be aligned along the electric field. One side will become minus, the other side will become plus. So I'm going to make big so you can see. So this is a positive charge. So that side will be minus, so it's pulling the electrons, and this one is going to be plus. So this is called polarization. But that becomes a dipole, but it's not a permanent dipole like water, and it's not conducting. Is that clear? So I have like a small simulation here somewhere. Somewhere here. So you have two plates here. So you connect those two plates to a power supply. And if you have non-conducting material, like a seed or a rice or whatever that is not conducting, it's going to get polarized and it will align itself along the electric field. So I can show you. So I emphasize that just the concept because I know it's important for chemistry. So let me make that big. So imagine here, imagine we have an electric field. So which way is the plus? Is this the plus or is it the minus here on that side? Huh? Electric field goes from where to where? Plus to minus. So here I could have a positively charged plate, and here I can have a negatively charged plate. And that's going to be your electric field. Now you place inside a non-conducting material, so it's going to be polarized. No. I rewind. So this is another example. I place a water molecule. Okay, I want to place a water molecule. Are you with me? Is a water molecule a dipole? Yes, because hydrogen gives away its electron, oxygen takes the electron. So the positive here, the positive charge, which will be the hydrogen, it will be acted upon by a force. That force will go with the electric field or against. A positive charge wants to go with, okay? And the force will be F equals QE, because what's the definition of the electric field is the force per unit charge for 1 coulomb. So if you have Q coulomb, the charge will be QE. Does that make sense? Now you see it's attached. Water molecule is not like loose. It's everything is combined together. So here you have the oxygen, say. So this is negatively charged. Now, which way wants to go, the negative charge? Against or with? Against. Okay, so even though it's neutral altogether, okay, so if you have a water molecule, even though it's polarized, it's still neutral. It's not like it lost an electron or gained an electron. It's just that the electron is one side leaving the nuclei on the other side. So one side is negative, the other side is positive, but it's neutral. Are you with me? So if you have this water molecule inside an electric field, what's going to happen to it? You see here? You see, imagine you have a string connecting plus to minus. This one wants to go this way, this one wants to go that way. So what's going to happen to it? It's going to turn, it's going to twist. Okay, there will be a torque applied to it. There will be rotation. Is it going to move? No, because it's neutral. Okay, it will be moving if you just have a plus by itself, then it will accelerate with the electric field. If you have a negative here by itself, it will go against the electric field and it will accelerate. But in that case, you have a dipole. You see, it's connected together, water molecules, so it will twist and it will align with the electric field. Do you understand? And now, if I do something horrible, so it try to twist this way, and all of a sudden I reverse the electric field, what's going to happen? It's going to twist the other way, right? So because that plus wants to be on that side, the minus wants to be on this side, because this is plus here and this is minus. Now, if I do something terrible, I reverse, I flip the electric field, right? So now the plus does not want to go here, it wants to go the other way. So it's going to twist the other way, right? So if I keep flipping the electric field, this way, that way, this way, that way, what's going to happen to the water molecule? It's going to not, maybe it will break if you put a lot of energy, but in that case, it's not going to break, but it will keep twisting, right? Twist, 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 twist. So that's how microwave works, right? Because when you have a microwave, so whatever you are trying to heat up has to be juicy. Okay, so if you put a stone, if you put a stone inside, it's not going to work. So you see what's happening. You inside the microwave, you have a microwave, and what is a microwave? It's an electromagnetic wave. What is an electromagnetic wave? It's made of an electric field that keep twisting back and forth, back and forth, back and forth at a frequency of 60 hertz, I guess, so up and down, up and down. So the dipole here will keep twisting back and forth, back and forth, back and forth inside your juicy thing. So what can happen to it? It's warmer, okay, because of friction. So that's how a microwave works. It's just because the water happened to be dipole, permanent dipole. So the electric field keep changing direction, so it's flipping. So the water molecule keep being apply a torque to it. Okay, so it keep twisting one way, the other way, one way, the other way. So all that motion turn into heat. So that's why if you put a stone or a piece of wood, it's not going to heat it up. You need something juicy inside. So you all know that if you put a pie, for example, the crust will stay cold. So you say, okay, I can bite, and then you burn yourself, right? Because it's only the inside that is juicy. So that's how it works. You see the electric field. So the molecule keep being twisted in one direction, the other direction. Plus the molecule can move. Okay, they are not pinned at one place. They can move because it's a liquid. So that's how it works. So if you have so if you have a dipole inside an electric field, it will twist in such a way that the plus here will face the minus and the minus here will face the plus. So in that case, which way is the electric field? To the left or to the right? To the left, from plus to minus. So if this is oil and you put little seeds, it's going to be polarized and it will twist until it's a line along the electric field. It works only, of course, if it's not conducting, because if not, it's not going to work the same way. So that's why you can use little seed to visualize the electric field, because all those little seed will be polarized, it will be twisted, and they align themselves along the electric field. Isn't that interesting? So these are like charges, and this one are unlike. So we talked about that last time. So you have a parallel plate capacitor. So this is a plate that is positively charged. This one is negatively charged. The electric field will go from plus to minus, so it's going to be uniform. And all those little induced dipole will align themselves along the electric field because there will be a torque applied to it. So here you have two like charges, and you see how their electric field is interacting with each other. So it's like they don't like each other, okay? So it's like you take a spring and try to squeeze it, so it's gonna resist you. So it's kind of the same idea. So I don't know. Okay, so here, let's take this. I'm going back to here. Hydrogen bonds. Can we do this one? I've lost my note. Okay, I'm back. Let's see. Let's go back to, let's go back to here. So remember gravity here? If you take a mass here inside gravity, what's going to happen to it? It's going to have a high potential energy. Okay, what's going to be the potential energy? Exactly, mgh, right? So in that case, you choose that your potential energy here equals 0. Let's say I want to find the potential energy per unit mass. It's going to be equals to what? Hmm? So for 1 kilo, what's going to be the potential energy for 1 kilo? So M equals 1, what do you get? M equals 1, what is left? GH. Okay? We didn't do that in physics 1, but you could have say, okay, I want to know what's the potential energy for 1 kilogram. So that will be the potential energy for per unit mass. Is that clear? So here, if I have a charge Q here, it's not happy, and you have a voltage here. So I don't know, let's say the voltage is delta V. Okay. So for example, here you could have 25 volt. Okay. Here you have 0 volt. Okay, so 1 coulomb of charge placed here will have an energy of what's the definition of voltage? So yes, okay, so that's what we're gonna get to it. So 1 coulomb of charge will have an energy of 25 joule. Remember from the test? Okay. So what's gonna be the force acting on it? F equals, so the force here was mg, right? So here it's gonna be, so no, yes, but what's the equation for the force? mass here, we have mg, yes? But we do not have g here. What is it that we have instead? Electric field. Okay. What is it that we have instead of the mass? The charge. So the force equals F equals QE, yes? And then if you want to find the acceleration, yes, you do QE divided by the mass. Don't erase your memory, okay? What I'm saying that. Okay, what about the potential energy? So V, the potential energy per unit charge, it's going to be what? Look, here it was GH. So here it's going to be E, E, H. Okay, it's still that. Okay, so what is that? Does that means? It's just giving you the relationship between voltage and the electric field for a parallel plate capacitor. Okay, this is energy per unit charge. So the potential energy, if you want, okay, I can also find the potential energy. So here it was mgh. So what is m here? It's going to be, instead of m, you have q, okay. What is g? Instead of g, you have e, okay. And I'm going to call that y, delta y, okay. So at that position here, so if I say the potential energy equals 0, the potential energy here will be Q E delta Y. That means that distance here. So it's exactly the same thing. Do you understand? You can call it H. That will be the potential energy of a charge Q here. If I let go, what's going to happen if this is positive? So it has potential energy. What's going to happen if I let go? It's gonna accelerate, right, to the minus. Why does it want to accelerate? Because it wants to decrease its potential energy. Now, this is working only if you have a uniform electric field. What's going to be the voltage? So we call that delta U. So what is the voltage? By definition, is the potential energy per unit charge, right? Don't forget everything. The voltage is the potential energy per unit charge, the energy per 1 coulomb. So you're going to have E delta Y. Okay? So that will work for a parallel plate capacitor. Okay. So let's take an example. Let's go back to here. So let's take an example there. So if you have a parallel plate capacitor, so let me show you what it looks like. Then you're gonna have you see, do you remember this? You are charging your capacitor. What is these lines here? An electric field. Is it a scalar or a vector? A vector, okay? What is the magnitude? That will be the force per 1 coulomb. So if you have 1 coulomb of charge, okay, it will be acted upon by a force equals to the electric field. So what do we have between the plates? We have a voltage. Okay, so you have a charge plus Q. Here you have minus Q, and you have a voltage across the plates. What does that voltage mean? It means that each coulomb of charge will have an energy of, very good, 1.5 joule. So this is potential energy. It's a potential energy per 1 coulomb. So if it's instead of having 1 coulomb, you have a charge Q, what do? You multiply by, this is per 1 coulomb. So if you have 2 coulomb, what's going to be the energy? 3 joule. You multiply the voltage by the charge to get the potential energy. Is that clear? If you have 3 coulombs, it's going to be what? What's going to be the energy of 3 coulomb? 4.5. Is that 4.5 if I know how to compute? Okay, so that will be the voltage. Now, look, do we have the distance between the plates? You don't have the distance between the plates? 10 what? 10 millimeter, which is what in meters? 10 to the negative 3 meters, right? So that will be the distance between the plates. I'm going to call that, what do you want to call it? H, D? Okay, big G or small g? Okay, small g. Okay, so I'm telling you then that the voltage equals E times G in that case. Okay. Let's compute that. So you have 1.5 volt equals E, the electric field. So this is only true for a parallel plate capacitor. In that case, otherwise you have to do calculus to find what's going to be the relationship between both. But in that case, it's going to be 1.5 equals to E times 10 to the negative 3. So E will be what? It's going to be what? 1500. Okay, so you see, I divide volt by meters. So it's going to be volt per meters. Or you have 2 ways to look at it, or you can say Newton per Coulomb. So you have 2 units for the electric field. This unit, okay, tells you that actually the electric field is the slope of the voltage. It means by how much the voltage decreases for each meter. Or you can think of the electric field as the force per one coulomb. Okay? So let's see if we have, we don't. I have to take this one. So it's a little bit messy here. There you do 1.5. Is that right here? 1.5 divided by 10. Look. What's the mistake here? What's the distance? Huh? It's 10 millimeter. So it's 10 times 10 to the negative 3. So that will be 10 to the negative, huh? Do it with your GI. 10 divided by 1000, or 10 times 10 to the negative 3. That will be 10 to the negative 2. That's 10 to the negative 2. That's 10 to the negative 2. So the answer is E equals 150 Newton per Coulomb. Yes? Are you with me? Do you see the mistake? It was not 1 millimeter, it was 10 millimeter. So 10 times 10 to negative 3 is 10 to negative 2. Yes? Okay. It's we are all tired, but we can do it. So, okay, let's measure the electric field to see. Are you ready? Are you ready? Look, I have an electric field sensor. What do you see here? 150 volt per meter. Okay? So you see how it's done? Okay, let's try to do this one. Number 26. Let's look at your equation sheet. Make sure you know how to use your equation sheet. You see here you have the Coulomb's force, okay? It goes as the inverse of the distance squared. You have the electric field in magnitude, it's going to be the force per unit charge. You have the electric field here, so it means it's the same thing. It's a force, but it's a force per 1 coulomb. And you have this equation here. E equals delta V over delta R, which is like a slope. So for a parallel plate capacitor, the electric field is the voltage across the plates divided by the distance between the plates. You see that? Okay, so let's go back to here. So did you do this one? Do it. I'm hungry. It's hard to focus. So you have two plates here. This is Q and this is minus Q. You see these two plates here. So these are plates and it's connected to a power supply. So I have a power supply that is providing a voltage V. So you have an electric field here between plus and minus. Okay, so this is plus Q and this is minus Q. You have charges all over and have charges all over. In between, you have a uniform electric field. And you have a relationship. So you will write distance lowercase d. You have a relationship between the electric field, the distance between the plates, and the voltage. Okay? Okay, so we have G equals 2 centimeters, which is 0.02 meters. Yes? Potential is 100 volts. So this means this is at 100 volt, this is 0. So that means the voltage drop here is 100 volt. So you have 100 volt voltage drop. So delta V or V, let's call it V, but it means delta V equals 100 volt. So you use these equations here, so what do you get? You sure? 100% sure? So E equals 100 divided by 0.02. So we divide by 2, so it's 50 divided by 0.01. So you write it will be 5,000 Newton per Coulomb, or in magnitude, it will be 5,000 volt per meters. So what it means? It means here, the electric field is showing you that the voltage is losing 5,000 volt per meter. Or 50 volt per centimeters, right? 50 volt per centimeter. So each time, so the voltage here is 100 volt. Let's say this is 0. So for each centimeter, you are losing 50 volt. Do you understand? So this is 2 centimeter and you have 50 volt per centimeter. So how much you're going to have here in voltage? So you are losing 50 volt per centimeter. So for every step of 1 centimeter, you are losing 50 volt. So how much volt do you have here? 50, very good. So remember, a voltage, you can think of that as altitude. You start with 100 volt and boom, there is a drop of 100 volt. The electric field, okay, you have two ways to look at it. You can say that will be a force. If you have 1 coulomb of charge here inside, it will be acted upon by a force of 5,000 Newton, because that's the definition. Or you can think of the electric field as a way to find out by how much the voltage decreases for every step. So in that case, you have centimeter. For every centimeter, it's going to lose 50 volt. Is that clear? And what is that? It's a slope. So the electric field is trying to bring a positive charge to a lower level of energy. So make sure you go over your textbooks. Very important you do the solve problem and so forth and so on. Okay, slide 55. Well, this one we already did things like this, right? So if you have an electron here, the electric field is from plus to minus. What's going to happen to the electron? Does it want to go with the electric field or against? Against. So it will be acted by a force equals Q times E, thank you, Q times E, okay? So it will accelerate, okay, from kinematics. But you can see here, this is minus, they repel each other. So this is a constant electric field, okay, it's uniform. So the electron will be acted upon by a force in magnitude equals QE. So it will accelerate and then it will miss the plate here because there is a hole. So it will keep moving. We talked about that when we talked about the proton therapy, for example, right? So you accelerate charged particles and the acceleration will be QE over the mass. You can even find the speed here. You can say v square equals initial square plus 2 times acceleration times the distance. You can do that, right? If you want to use kinematics. Okay, talking about energy, remember from physics 1, you have kinetic energy, and that will be rotational kinetic energy, that will be gravitational potential energy, that will be elastic potential energy, and finally we have electric potential energy. Okay, so energy is always relative to a reference level, and just as we have seen, if the voltage is energy for 1 coulomb, so the potential energy will be Q delta V. Does it make sense? Again, if you have a 12-volt battery, what's going to be the energy of 1 coulomb of charge? 12 joule. So what is happening inside the battery? There is chemical reaction and everything happens like every single 1 coulomb of charge is raised to 12 joule. Each coulomb of charge is raised to 12 joule because of the chemical reaction inside the battery. And then that energy will be delivered to the load, right? So if you have 3 coulomb of charge, how much energy, potential energy, will be 12 times 3. Is that clear? So that will be the potential, the electric potential energy. That will be your voltage, and that will be the charge. Yes? So once a charge has potential energy, that potential energy can be turned into kinetic energy. Very good. So imagine this room here. So you have this ceiling is positively charged, the floor is negatively charged. So you have an electric field from the ceiling to the floor. If you have a positive charge here, is it happy? No, it wants to go down because this is negative. It wants to go with the electric field. So all that potential energy, Q delta V, so that will be the voltage between here and the ground, Q delta V will be turned into kinetic energy. Very good. So it's very much like height. Potential is like height. Okay? So that will be the definition for potential energy. Okay, so let's try to do, go ahead. You're staring, don't stare, do it. We can help each other. So maybe you're gonna have 1 volt here, and here maybe you're gonna find a way to emit a proton. So here you have like 1 proton here, so that will be E. And this is negative. Okay? So what happened to this to this proton? Is it going to stay chill out here or what? It's gonna go to the right because it wants to go with the electric field. So it's gonna be acted upon by a force equals QE. Right? Yes or no? Okay, so the potential is 1 volt. So 1 joule per coulomb. So what's going to be the potential energy? So the potential energy is Q delta V, right? Because this is for 1 coulomb. So you have that much of charge multiplied by Q. So that will be the potential energy of the proton placed in that electric field. So it's like the potential energy of a mass above the ground. So it has potential energy. Remember, voltage means energy for 1 coulomb. So the energy for Q coulomb, you just multiply by Q. Does it make sense? All that potential energy is going to turn into kinetic energy. So how can I find? So it's going to accelerate here. Yes, so it's going to be half mv squared, but that's not what they are asking. They just want you to find the kinetic energy when it's there. So how much kinetic energy is going to gain? That's going to be equal to the potential energy it has lost. Potential energy goes into kinetic energy. So mgh equals kinetic energy. Oh no, again. I hope there is no coffee. Okay, let's do it. Come on, come on. So what's the charge of a proton? Okay, times what? 1 joule. That's it. That will be turned into kinetic energy. Yes? So then if it starts with a from E, okay, you could say also, you can say, so that will be if you use joule, okay? If you don't want to use joule, so you say, okay, my Q is gonna be E times 1 volt, so I'm gonna have 1 EV. 1 eV is the same thing as 1.6 times 10 to the negative 19 joule. Okay, so 1 eV, it's a unit of energy, and that's going to be this. Remember, we talked about that with the X-ray machine. You have 50,000 volts, so 50,000 eV. That will be the potential energy that will turn into kinetic energy. Yes. Yes. Yeah, but here they talk about the mass. We don't care about the mass. The proton has the same charge as an electron. They try to trick you. Okay, but by the way, this is a typical MCAT question to confuse students with TMI. This is TMI. You don't need that mass. Okay, it's just to confuse students. They love to do that. But how can we use this information? Let's say now they tell you, okay, the velocity of the proton is 0 to begin with. What's going to be the final velocity when it's going to crash here? So then you're going to say potential energy will turn into kinetic energy. Okay? So you're going to say 1.6 times 10 to the negative 19 equals 0.5, the mass of the proton, okay, the final speed square minus initial kinetic energy, but it's 0. And from there, you can find the speed. Is that clear? And now you can use the fact that the mass of a proton is like 2,000 times the mass of an electron. And I always forget it's something like this. I think it's like something like that. Is that clear? So it's good that you bring that question because sometimes some questions have TMI, just to confuse you. To get a curve, right? They like curve. Okay, let's do this one. Okay, now you can help each other and try to solve this one, number 2. So here too, they give you TMI. Yes. Which last one? Yeah, it was 1.6 times 10 to the negative 19 joules or 1 eV. eV. So here you have a positive charge. So first thing you want to draw, okay, you have a positive charge and it has an initial velocity. Okay, initial velocity here, 55 meter per second, and you accelerate. So it means somewhere you're gonna have a minus here. So the voltage here is 500 volt. So that means you do have an electric field here going from plus to minus. So this is your electric field here. So it's going to be acted upon by a force. Okay, so it's going to accelerate. It's going to gain kinetic energy. Why does it gaining kinetic energy? Because it had potential energy to begin with. What's the potential energy? So it's going to be delta V 500 is per Coulomb. So if you have Q, it's going to be Q delta V. So that will be its potential energy. Okay, so before you let go, it has that much of potential energy. Oh, it had kinetic energy to begin with, but we are just asking the change in potential energy. Okay, so the change in potential energy is Q delta V. So can you do the computation? What did you say? 2.5? 2.5 times 10 to the negative 3 joules. Yes? Yes? That's how much potential energy is gonna lose. And that will turn into kinetic energy. So all that potential, okay, it's losing potential energy, it's gaining kinetic energy. Okay? Now, if you want to find the final velocity, then you have to use this information here. Okay, because you say, remember from last semester, so the change in potential energy equals to the change in kinetic energy. And the change in kinetic energy will be the final kinetic energy minus the initial potential energy. Do you remember that? So 0.5 times the mass times v squared minus v sub 0 squared, okay? And then you can plug your 55 into there and solve for v. So that will be algebra. And then physics stops and you can find the final speed. Is that clear? So if you understand gravity, it works the same way when you have a uniform electric field. So if you go back to the cathode ray tube, for example, that you use you use that to make X-ray. I don't know if I can make it bigger. Do you see? So these are electrons. So if these are electrons, that electrode is what? Negative or positive? Negative, okay? Because it's going to push the electron toward the blah, 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 positive. So the electric field, so this is plus electrode, negative electrode. The electric field is going to the left or to the right? To the left. So the electric field is always riding against electric field. If the voltage applied is 10,000 volts, what's going to be the energy of an electron? 10,000 joule per coulomb. So you have 10,000 times the charge of an electron. So in EV, it's going to be 10,000 EV. Okay, so 10,000 volt means 10,000 joule per coulomb. The charge of an electron is E, so you have 10,000 EV. All that potential energy is going to turn into kinetic energy. There is a hole here, so it has inertia. Okay, so once it's done accelerating, okay, it will keep moving at a constant speed and it's going to crash here. So if here you have like a special heavy metal plate, all that kinetic energy is going to turn into X-ray. So that was done by 19th century Röntgen. Röntgen, he did that experiment by chance and he discovered X-rays. And they didn't know what were X-rays, so they call it, when you don't know something in math, you call it X. So X-rays. They didn't understand what it was, but they did understand that if you put a hand here, so you put the hand of his wife, you're not taking chance, I take my wife. And it was the first X-ray ever taken because he could see the bones and the ring of his wife. And he said, I have seen my own death. Because it was for the first time people were able to see the skeleton, right? So it was a big breakthrough. You can look it up, X-rays.
To demonstrate a Crookes tube, a cathode ray tube, we need a high voltage power source, such as this one.
Okay, so
we need the Crookes tube, which has a metal cathode, a metal anode, A screen that has been coated with a phosphorescent material that gives off light when struck by electrons, and a bar magnet. As we turn on the screen, we notice that electrons are emitted from the cathode, and as they strike the fluorescent screen, we're able to see the cathode ray, this stream of electrons illuminated.
So that's how the electrons were discovered by J.J. Thomson. Okay, so you have a cathode here that will emit electrons. You apply a voltage, the electron will accelerate, and you can visualize the beam of electrons. Isn't that amazing? So that was cathode ray tube. I think we talked about that during the history, first class. Okay, so let's do this one now. Now you can do it. Okay, I give you some time so I can turn my. So again, potential energy turn into kinetic energy. Okay. So if it's accelerated, so that means here you have a cathode, and here you have an anode. It's like the cathode ray tube, and between them there is a voltage of 1500 volt. So this is the cathode, this is the anode. So this is negative, this is plus. So the electric field goes this direction. So the little electron here will want to go this way. It wants to go against the electric field. This is a little electron here. Okay, so don't stare. So the potential energy equals by definition of potential or voltage Q delta V. Yes? Okay. So what you get? 2 point. Very good. You said that. Yes. Right. 2.4 times 10 to the negative 16 what? Cookies? Joules. Okay? Or another way to write it, it's 1500 EV. E because it's the charge that I'm not replacing by 1.6, okay? So if you are going into X-rays, radiotherapy in the medical field, they use EV. They don't use joules, because joules you have to deal with scientific notation. Okay, so all that energy is going to turn into kinetic energy, right? So that will be equals to potential energy equals the change in kinetic energy. And the change in kinetic energy equals to 0.5 the mass V final square minus V initial square. And it starts from rest. So that means initial velocity equals 0. Okay, so do it. So delta U equals 0.5 times the mass times V square. So 2.4 times 10 to the negative 16 equals 0.5 times the mass 9.11 times 10 to the negative 31st and V square. Is that clear? Okay. And then it's TI. So physics stops, TI takes over. So the only challenge is to know how to use the TI, 2.4 times 10 to the negative 16, close the parenthesis, enter to make sure you divide by 0.5, enter, and then you divide by, open the parenthesis, 9 times 11 times 10 to the negative 31st, close the parenthesis, make sure you always frame the denominator, enter, and then you take the square root, so the second square, you call back the answer, so second minus, and that's something like this. Did you get that? 1, 2, 3, 4, 5, 6, 7. So 2.3 times 10 to the 7. Yes? Did you get that? It's easy to do mistakes here with the TI, so make sure you get it right. If you are not sure, you can change the mode to scientific notation, or you just go back until you find a number between 1 and 10. So it's very fast, okay, because the speed of light is 3 times 10 to the 8 meter per second. So if you take the ratio, you see what's the ratio? That's the speed of light. Oh, do we have the answer somewhere? Yes. Yes. No, so if they want to make it more difficult, like in the previous question. So let's say now V sub 0 is not, but usually it's 0 because you start from the cathode. So it means here you have a very hot filament, and it's so hot and it's so thin that the electrons, they can break free. Once they are free, they're going to be accelerating. So usually V sub 0 is 0. But if they want to make it tricky, so then they will say, okay, initial velocity is 55 meter per second, then find V square. So in that case, you will have to do 2.4 times 10 to the negative 16 equals 0.5 times the mass times v squared minus 55 squared if you have an initial velocity. And then you have to divide this by that, and then you have to add the 55 squared, and then you need to take the square root. Yes, everyone? So that will be a little bit more challenging. Okay, so here it's from the book Johnson and Cotnex. That's the book I recommend. You here it says the wording. The only challenge is the wording. So it says the electric potential at A. So electric potential is at a location, right? So it's a property of a voltage is a property of 2 points. 25 volt greater than at B. So the potential here is 25 volt greater than B. So if you put a positive charge, okay, it's gonna accelerate because you have a delta V between those 2 points. So can you find the speed? So you have your particle here, okay, the potential is 25 volt above B. So delta V equals 25 volt. So you need to find the potential energy that will be turned into kinetic energy. You see, it's from your book. The book I say that you should get. Or did I tell you that you have a website where you can find all those textbooks for very cheap? It's called thriftbooks.com. thriftbook.com. Okay, so the difference between A and B, so VA minus VB, so that will be your delta V, is 25 volt. Okay, and here you place a charge plus Q. So Q equals 3 times 10 to the negative 5 coulomb, right? So your potential energy will be, by definition, Q delta V. Yes? So it has potential energy and it wants to go to a lower level of energy. Potential energy is like voltage is like height. Okay, you want to go from high up down there. So Q delta V, so it's going to be what? Times 25, right? Which is, yeah, who said that? Yes. What's your name already? Me? Huh? Mattel. 7.5 times 10 to the negative 4 joules, yes? All that potential energy is going to turn into kinetic energy. So 7.5 times 10 to the negative 4, we start from rest. So that's going to be 0.5. The mass, we have the mass, so 1.8 times 10 to the negative 5 v squared. So you can find it's a 5 here. So you can find the speed. So how much is that? Yes, 9. So do you all know how to use your TI for that? Yes? And because it says on the slide here, it is released from a point A, so it doesn't say it's shown. It means it's released from rest, and then here it says 0, right? And so if you go back to the slides here, see kinetic energy 1/2 mv squared. You have your kinematic equations here. You have Newton's second law, and we have been using here electric field is delta V over delta R. So in the parallel plate, capacitor will be the distance between the plates. And you have delta U equals Q delta V. So make sure you know how to use the equation sheet. Okay, is that clear? Oh look, I modified I modified the slide actually over the weekend, so you can see the book where you can find it. Thrift books. It's very cheap. Now, if you do the opposite, now if you put a negative charge wants to do the opposite, okay? Positive charge wants to go from high potential to low potential. Negative charge wants to do the opposite. It wants to go from low potential to high potential. Why? Because high potential means plus. Minus wants to go to plus. So a few applications here. So for example, there is a technique to sort out segments here of DNA. Some pieces of DNA will be longer, so more mass, and some of them will be less mass because they will be smaller. So you have large fragments of DNA and small fragments of DNA. So you apply a voltage here. So since you are so good at biology, remember DNA is charged negatively, right? So it's negatively charged. So the electric field goes from where? From the minus to the plus or plus to the minus? plus to the minus. So if you have DNA that is negative charge, it wants to go which way? To the right or stay where they are? To the right, because they want to go against the electric field. Is that clear? And then it's inside some kind of gel that produce some drag. So the large fragment, after a while, they will stay behind and the small fragment will stay ahead. So that's how you can sort out DNA fragments. Isn't that interesting? So all of them will be acted upon by a force QE to the right, but then they will be slowed down because there is some gel here to the left. So the one who will go farther forward will be the small one, and the big one will be left behind. You see? Another application, I think I talk about that. I think it's called an elephant fish. I'm not sure, but you see, what is that configuration like this? The da 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 dipoles. Yes, it's a dipole. I don't have a dipole here. Is that a dipole? Oh, look at that. It's a dipole, right? So you see the electric field goes from plus to minus. You see, it has this configuration. So here it's able, I'm not sure how it's doing it, but it's like a dipole. With this electric field, it can detect, it can know if it can probe its environment. So if it's something good to eat, it's a conductor. The electric field cannot go inside, okay, but it will be magnified. If you have a non-conducting stuff here, which is like a stone or something that is not living, you see the electric field can go inside, but it's going to be polarized, so the electric field will be weakened. So it will be able to tell the difference. This you can eat, this you cannot eat. Got that? No, there was a silence here. Yes. So let's say you have an electric field going this way, yes? So you can imagine this is plus here, yes? Okay. I told you when you have an electric field, then the electric field can go through the not conducting material, yes? You're going to have an electric field going through, yes? Okay, so this is plus. What's going to happen if you put something not conducting in an electric field? You're going to get polarization, right? So all the minus here gonna be here, and all the plus is gonna be there, yes? So inside that material, so I'm gonna make the material here, I'm gonna make it big. Okay, so it has minus here, plus here, because it's not conducting, so it gets polarized. So it's making its own electric field. Which way it's gonna go, its own electric field? From plus to minus. So this electric field inside will weaken the electric field outside, because this electric field goes this way, that electric field goes up, so this electric field goes down, this one goes up, so they cancel each other. Okay, so you're going to have less electric field here. Do you understand? Can we have an electric field inside the conductor? Never. It's always safe to stay in your car when you have lightning outside. So there is no cancelling effect. All the electric field here will be perpendicular to the living thing. There is no electric field inside. Do you understand? So what does it mean? Again, if you have an electric field, okay, and you have something that is not living, so this is not living, it's a stone. Can the electric field goes inside? Yes, but here it will be, so imagine that's plus, because always from plus to minus, because it's not a conductor here. What's going to happen? It's going to be polarized. So you have minus here, and here it's going to be plus. So now you have an electric field from here to there. So that electric field will get weaker because there is something against it. Do you understand? Now, if you have a leaving field, the electric field cannot go inside because it's a conductor, so it won't be weakened. So anyway, the only thing you have to remember, if it's not a conductor like this, the electric field will be weaker. Doesn't mean that you have no electric field, it's just weaker. You see, that's why it's farther away. If you have a living thing, then the electric field will be stronger. So now you can understand that's marine biology, kind of, right? You see, if it's a conductor inside an electric field, the electric field cannot go inside. It will be polarized as well, but it cannot penetrate. If you have a non-conductor, the electric field can go inside and it will get weaker. So that's why you have more spacing between the lines. Is that clear? Okay. So the point is that it's very important to understand electrostatics for anything biology or medicine and things like this. Okay, other interesting here, DNA. You see you have one base with the other base, and these are called hydrogen bond. So what's happening when you have a hydrogen bond? It happens between hydrogen oxygen or hydrogen and nitrogen. Because the oxygen wants to take the electrons of the hydrogen, or the nitrogen takes the electrons. So you can see that here. You see here that you have a T and you have an A. You see oxygen here takes the electron of the hydrogen. So they hang out together. They are not really attached to each other, but they will be attracted to each other. So it's a bond. It's called a hydrogen bond, even though it's like invisible, but you still have a bond here. Or it can also happen between nitrogen and hydrogen. Is that clear? So you have a dipole. Minus goes with plus. It's like this one is stealing the electrons of the hydrogen, and the hydrogen say, no, 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 give back my electron. So it's just chilling out with it, okay? It's not going to go anywhere. It's a bound together. They are bound together. So that's how it works. So all those connections here happen because electrostatics force between hydrogen and oxygen or hydrogen and nitrogen. Okay, so I think I talked about that also. Did I? I think I did, right? Also thanks to electrostatics. So there is a technique called AMT. If you want to deliver a drug to the brain, so it's very hard to cross the blood brain barrier. So you have different techniques to do that. So first of all, you need to use lipid nanoparticle because the brain loves fat. You have a lot of cholesterol in the brain. That's why, the milk of the mom has a lot of cholesterol because we need the cholesterol for the kids to develop their brain. It's very important. So anyway, anything fat wants to go to the brain, and plus here it's being positively charged. So here, that's how I can cross the brain barrier. So I don't know the details, okay? All I know is that electrostatics is involved. If you want to have more details, you can do your research about AMT. Is that clear? And here I have no clues, no clue what's happening. That you have to need to ask your biology professor. Okay, so Xerox copy also works because of electrostatics. I think I talked about that. That works because of electrostatics as well. Okay, let's do more problem. It's a review problem. Go, 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 go. You have to draw. You cannot do it like this. Okay, you have to draw. Okay, and remember, you have the equation sheet here. Remember, electric field, this here, I forgot to tell you, 1 over what it's called 4 pi epsilon 0, that means K. That number here means 9 times 10 to the 9. It's the electric constant. Okay, did you hear? That number here is just 9 times 10 to the 9. It's the electric constant. Let's go back to my slide. If you want, I can explain again the fish, if you're interested, at the end. So you have a point charge, 2 nanocoulomb. So it's gonna be the source for an electric field. As you move away from the charge, you see the electric field gets weaker. That's why the lines are farther away. Okay. So that will be the electric field. And you are looking at a distance r. So here at a distance r, so that's my distance r equals 5 millimeter. And you want to know the electric field here at a distance r. It's the inverse square law. So the electric field is by definition. If you want, you can say, okay, I put 1 coulomb of charge here. What's going to be the force? So it will be K, Q, it's the source, 1 coulomb if you want, over the distance square. By definition, then you look back to your equation sheet. Okay? So you just plug it in. So that will be 9 times 10 to the 9 times the charge 2 times 10 to the negative 9 times 1 and 5 millimeter. You replace that by a negative 3 and that's going to be square. Okay? Don't stare. Do it, 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 do it. That will be in magnitude. Are you doing it? So by the way, that goes away. So 9 times 2 divide by, open the parentheses, 5 times 10 to the negative 3 square. Do you get that? Yeah. 1, 2, 3, 4, 5. Yes? Do you agree? You sure? So 7.2, who say yes? Yes? Yes, you all agree. Newton per coulomb or volt per meter at that distance here. And then as you move away, it's going to decrease. What is the force? So what's the force? The force equals QE. Okay, so it's going to be pushed away. So if you have your charge, you have a charge here. No. It's a negative charge. Look at that. No, I want that blue. No, I already have blue. Here. Negative 0.250 microcoulomb. So which way is going to go? So is it going against the electric field or with the electric field? Against. So it's going this way, right? I mean, going this way. Of course, because this is plus, this is minus, so they're going to be attracted to each other. And so here it's just the magnitude, okay? So it's going to be 0.25 times 10 to the negative 6 times 7.2 times 10 to the 5. Okay, so you take your electric field from your TI and you multiply by 0.25 times 10 to the negative 6. and you get 0.18. Did you get 0.18? Okay. 0.18 Newton. Okay? And it's gonna, if it's placed here, it's gonna accelerate. Okay, let's do the next one. Next one you have to draw. You mean in here? So it's not that you want to get rid of the negative, it's just that will be the magnitude. The negative is here to tell you, okay, that that's a good question. It's just gonna tell you that they are in opposite direction. So if the electric field is this way, the force will be in the opposite way. Right? So if you have two vectors A and B, if you have A equals minus B, it just means if A is this way, B will be the opposite. That's what it means. It's a good question because actually these are vectors. Okay, let's do this one. You just arrived. You just arrived like 3 minutes before. You're kidding me, right? You're not supposed to do that. Next time you don't do that, okay? If you come late, you come late, you don't mark present. So this is the electric field. No, that's not electric field, that's a force. Okay, so try to do it. So you have a negative charge, minus 1.75 microcoulomb, and it's acted upon by a up force. I'm going to do this. F is up. So F is up. Where is the electric field? A negative charge wants to go against or with. Okay, so where is the electric field? Up or down? Down. Okay, so now in magnitude, once we have deal with that, we have F equals QE. So now you can find E. Minus 5 divided by 1.75 times 10 to the negative 6. And you get, I get that. Did you get that? Okay, good. Or 11.4 volt per meters. Okay? So you just apply, you just plug it in. Okay, let's try to do the next one. I have an eye on the clock. Oh, east. East is where? This is west. This is west. This is east. The electric field is east. So the force will be where? It's gonna be the force, a positive charge. Does it want to go with or against? With. So the force will be east. So F will be Q times 250, and the unit will be Newton. Okay? We are almost done.